All right, here we go. So exercise 13C, exponential graph notes. Here we go. What you see here is a general equation for the exponential graph. Exponential is anything that has a power. So in this case, it's b to the power of x. That is your typical exponential equation. Your textbooks might use different letters. They maybe call it A, for example. I'd just like to go in alphabetical order, so I go A, B, C, D, but it doesn't really matter. Now, let's have a look at each of the letters that I have for you, and we explore what it does to the graph. We're going to start off with the easiest one. Let's see if you remember D. When you add or subtract something to a function, what does it do to the graph again from chapter 7? Hands up if you remember. Yes. Moves it up or down. So write that in. So it moves it up or down. The technical name is called a translation. It's a vertical translation. When does it go up and when does it go down? Hands up. Anyone know? So we know it goes up or down. Christina? Good, so put a note in. When it's positive, so if D is positive, the graph will shift up. And when it is negative, it will shift down. Next one. I'm going to highlight it. The end times bracket x plus c. Now, I taught you this transformation. I taught you a way to solve if it moves left or right. How do you find out if it moves left or right again? What do you have to do? Make it equal to 0. So that C technically tells you if it moves left or right, but how do you solve it? I want you to always let whatever because that's where the original x is. See that? That's the original x. So b to the power of x makes it exponential. What you're changing is the power. So every time there's anything to do with the x, I want you to let that equal to 0 to find out if it moves left or right. Okay, so here, write in, let n bracket x plus c equal to 0, and then solve for it. Solve for x. Now, if x is positive, then it moves to the right. If x is negative, it move left. And then just one more note before we look at the graph so you can see the up, downs, and left, rights, and then we'll talk about the A's and the N's afterwards. But B is your base. It's the base of the exponent. And that just dictates the rate of how fast it grows. So I'm going to write here, this dictates the rate. If in an application question, you usually get something like, they say, a bacteria doubles itself every hour. Okay, the doubling, that's the base. So you're timesing yourself by 200, like you're doubling it, so hence 200%, or you're timesing it by 2. Okay, so that rate, so it's times 2, times 2, times 2, or if you're tripling it, it's times 3, times 3, times 3. Because remember, index laws is based on the repeated multiplication. So if you do 2 to the power 3, it's just 3 times 3 times 3, right? If you do 2 to the power 5, it's 2 times 2 times 2 times 2. So the idea is, whatever rate it is, so the rate of change, so in this case, whether it's every hour it's halving, every hour it's multiplying itself by 2 or a factor of 3, that's what the B stands for. So it dictates the rate of the graph. So let's have a look at Desmos. I'm just going to go to Desmos. Here we go. Let's visualize this. So y equals 2. I'm going to do b to the power of x just to start off with. And let's make b a rate of 2. Okay, so if I said b is equal to 2, that just means I'm saying 2 to the power of x means double itself every hour or every minute. Okay, so you can see that if I zoom in, in the very first hour, when it's 0, so it's 2 to the power of 0, it's 1. That makes sense why you have a 1 except at 0, 1, because if b was 2, 2 to the power of 0 is 1. Index law number 6. Yeah? After 1 hour, then it will be 2 to the power of 1. So 2 to the power of 1 is 2. After 2 hours or 2 minutes, for example, then it will be 2 to the power of 2. So it's 2 times 2. 2 times 2 now becomes 4. But then you double yourself every hour. So by the third hour, you're going to double 4. Or 2 times 2 times 2, then it becomes 8. So you can see it goes 1, double of 1 is 2, double of 2 is 4, double of 4 is then 8. This is called an exponential graph, which you can see. Yeah, and obviously if you go into the negative side, let's have a look. Let's just do a bit of an exploration here. So I just gave you an example of y equals 2 to the x. We just saw that on the graph, when it's 1, it was 2. When it's 2, it was double of 2, which became 4. Then when it was 3, we know that it's going to double 4, and eventually it's going to be 8. So it's growing up really fast. Okay, it's going up really fast. And then obviously at 0, it's 1. What happens when you go to the negative? Well, let's have a think. When it's negative 1, that's 2 to the power of negative 1. But your index law number 7, which is from yesterday's lesson, what's 2 to the power of negative 1 the same as? Half. It's 1 over 2 to the 1. But then the further I go to the left, if you think about it, if I go to negative 2 and then I go to negative 3, you're really just saying 2, negative 2, and then 2, negative 3. Each one becomes 1 over 2 squared, 1 over 2 cubed. Even though denominators are increasing, yes, that becomes 4, that becomes 8, that becomes 16, and double 16 is 32. The problem is, even though the numbers get larger, but if the denominators get bigger, what happens to the overall value? Does it get bigger or smaller? Smaller. As you can see, it's 1 over 4 is smaller than a half. 1 over 8 is smaller than a quarter. So what you're really doing is, as you're moving to the left, notice that you're halving it. Half of a half is a quarter. Half of a quarter is 1/8. Half of 1/8 is 1/16. Okay, so what you're really doing is, as you go into the negative side, it actually gets smaller. Oops. It gets smaller, and what's happening is the rate is the inverse of what you were doing. So you were saying double when it's positive, but then when you go negative, it's halving. If it was a rate of 3, it would be tripling, and then 1/30 in the negative direction. Make sense? Okay, so far, what have I shown you? That's B. So I can change B, and look what happens when I change B. It just changes the rate. So if I made it 3, it just means starts off at 1. After 1 hour, it triples itself. So the triple of 1 is 3. Triple of 3 should be 9. So by the time I get to number 2, you should see here at 2, I expect the value to be at 9. And all of that, that's all it's doing. It's just 3 to the power of 0, 3 to the power of 1, 3 to the power of 2, 3 to the power of 3, and it follows on. Yeah? And we expect the same thing when it goes to the left. At negative 1, it should be a third, and a third of a third, and a third of a third of a third. Okay, and it just keeps going. Yeah? Now, let's add in the things that we've just explored. We said, if we add in a number, it should go up or down. So here we go. I'm going to change it back to 2, because 2 is just a nicer number. Watch when I add in now, y equals 2, b to the power of x, same thing. But I do plus d. Okay, so we said if we add on a number, it should shift the graph up or down. So watch what happens when I press play. You see that graph? When it's minus, it shifts the graph down. When it's positive, it shifts the graph up. Okay, so the plus D will tell you if it goes up or down. Now, there is a certain value. Let's just change it to 2. There is a certain value that it approaches. You know how in last term we learned about asymptotes? Can you see this one? On the left-hand side, when at the beginning, every time you halve it, it's impossible to halve a number to get to 0. You can keep halving numbers. So half of a half is half of 0.5, and then half of 0.25, and then half of a quarter is 1/8, and half of 1/8 is 1/16. Technically, you can go on forever. That means an exponential graph has one property that you always have to sketch in. It can never equal to the horizontal asymptote. So in this case here, b to the power of x, if it's 2 to the power of x, it can never equal to 0. Because every time you go to the left side, every time you're halving or thirding or quartering or a fifth, you can never a fifth, a 0. You never get a 0. You can always make it smaller. And because of that, that means the property of your graph, there needs to be, you have to sketch in y equals 0, 0, horizontal asymptote. And that just means you will never have a graph that touches that horizontal line. What's interesting is that if you shift up the graph, if you said +2, notice that the asymptote also changes. See, the asymptote before was at 0, but because I shifted the graph up by 2, I said plus d, and d is 2. Notice the asymptote now never reaches 2. So how do I show that? I can do this and say y equals d, and I'll make the graph with a dotted line so that you can see that's the asymptote. I'm going to make it green and dotted. Here we go. As I increase d, can you see how the asymptote follows? Because the graph never touches that. Okay, because that's all I'm doing. The very beginning was when d was 0. The asymptote is at 0. And all I did was I said, well, y equals 2, whatever you add or subtract. If you move it up by 5, then the asymptote is at 5. If you move it down by 2, then the asymptote is at -2. Does that make sense? So here's an example. If I changed it to -2, can you see how the graph will never touch at y equals -2? Because it started off at 0, that's where the original asymptote was. Never touches 0. If I shift the graph down by 2, the asymptote goes down by 2 as well. Okay, so you can see I can zoom in, and every time I zoom in, it just never touches that line. There's always that line. Every time you zoom in, there's a gap between it. Okay, it just never touches it because you can keep making it smaller and smaller and smaller. So that's why you have to draw the asymptote. So I'm going to zoom out. So far I've taught you rate, base, up and down. Let's have a look at left and right now. It's the same concept. I'm going to make D0 again just so you don't get confused by it. So here we go. That's our typical 2 to the power of x. Let's see what happens now if I put in a plus c. It should be up here. Plus c. All right. So remember how I told you, let whatever you're changing to the x equal to 0. Solve for x. Okay, so in B, whatever you change for the power, let that equal to 0. Solve for x. If it's positive, it should go to the right. And if it's negative, it should go to the left. So watch what happens. If I change c to 5 or 4. If c is 4, that means now it's x plus 4. So let's do what I just taught you. X plus 4, if you let that equal to 0, what would x equal to? -4, very good. But -4, if it's negative, it means it should move to the left. When you look at the graph, can you see how it's moved to the left there? If the original point was at 0, 1, if you move it to the left, I expect that now it should be -4, 1. See that? So the original graph, you had 0, 1, that's your y-intercept. It's right there. But if I shift it to the left, well, that particular coordinate should now be at -4, 1. There we go. I literally moves everything to the left. Everything goes left by 4. Okay, because that's what you're saying. That's what you're doing to this. You're saying whatever x coordinate is, when you add 4, when you solve it, it tells you how much you're moving. So you're moving to the left by 4. Okay, so everything shifts left by 4. So if I press play on it, you can see more positive value goes to the left. Once the C value is negative, it goes to the right. And here we go, back to the positive, so it's on the left side. And as soon as I hit negative, it goes to the right side. Okay, so if I put all C and D together, you'll see this circular motion. It goes up and down, left and right, up and down, left and right. But the shape stays the same. So I haven't made it thinner, I haven't made it wider. It's exactly the same shape with the same asymptote. It just moves left and right. Okay, so that's what C and D does to the graph. Let's pause the video, or more like the C's and D's. I'm now going to make this all zeros just to bring it back to the original. That to me, out of all the transformations, C and D is the easiest one to read. Okay, so C and D is the easiest to read because you're just moving left, right, up and down. The one that's a bit harder to understand is your N and your A because it makes it thinner, it makes it wider. So here we go, let's write some notes in. A, let's start with A because I think A is a bit easier to understand from your previous knowledge. Let's write A. A is a reflection if it's negative. So if A is less than 0, means if it's negative, it's a reflection. But what type of reflection is this? This is going to be a vertical reflection. What that just means is whatever the shape is, I want to flip it upside down vertically. Okay, so it goes up and down. But not only that, the reason why A's and N is tricky to understand is because not only is A responsible for a reflection, it is also responsible for a stretch, which we call dilation. I like to say AKA, which is also known as vertical stretch. The larger the number, so I'm going to write here, the larger than 0, so the larger that it goes. So if you made A 10 to 1,000, it should be a much larger vertical stretch, meaning it looks really thin. Okay, so it looks really thin. So I'm going to write here thin just to help you remember it. Larger the number, the thinner it becomes. The smaller the number, which means it's fractional, so like half, a third, 0.5, 0.2, 0.111, or 0.0001, the smaller the value. So it's bigger than 0, but smaller than 1, so it's fractional. Decimal. Any number like that, it should then be, well, not so much like it's being stretched out, but it's really just a vertical compression. So rather than stretching it up, you're now vertically compressing it down. Okay, so I'm going to say here, this feels like it makes it wider, but really, I want you to write on the side, it's a vertical compression. So think of it as squashing it down vertically. So if you squashed it all down vertically, what will change? And I'll show you the difference, why it matters between vertical squash versus horizontal squash, because it does make a difference. Okay, you'll see the difference in the shape of the graph. Here we go. We're going to go back to A once you've copied that. So larger than 0, meaning, or maybe I should say larger than 1. Sorry, I'll change that. Larger than 1, so the bigger than 1 it is, so 2, 3, 10, thousands, looks thinner. Between 0 and 1, it feels like it's getting compressed, so the graph looks like it's wider, but it's really just the vertical compression. Okay, so let's have a look. Watch what happens when I put now an A value in front. So I do capital A times. All right, it says add slider, so I've just done it. So I've just put in a capital A. So here, where's my slider? Here, that's my slider, capital A. Watch what happens when I increase it bigger than 1. So currently it's 1. As I move it can you see how it kind of looks like it's moving away? But watch what happens here. See? Can you see how the graph looks thinner? It shoots up. So if I change A to 1,000, you see how it just shoots up? It's like me stretching it up. Yeah? In a way, it almost looks like it's moving away from the x-axis. And that's one of the language that you learned last term. It's dilation from the x-axis, because you're moving away from the x-axis. Yeah? So if you have a look, now one of the key features, have you already noticed? One of the special things. See how it's 0, 1? If you're doing a vertical stretch, you're affecting the y values. So whenever I times to it, it should change that y coordinate. That's why the intercept has changed now. So the intercept is no longer at 0, 1. That graph has a different y-intercept. So where would it be? So if I made it back to 10, you see how it used to be at 0, 1. It's now at 0, 10. Right there. Why is it 0, 10? Because you're actually timesing. When I change that big A to a 10, I'm actually just saying whatever that y value was, I'm timesing it by 10. So at that point, 0, 1, it becomes 0, 10. Okay? Whereas if I change A to like a point, like a decimal, so between 0 and 1, if I did 0.5, can you see, right now, if I change that now, that's now 0.5. Right there. Because it's a vertical compression. So you either vertically stretch or vertically compress. That's what big A does. Okay, so that number that you multiply into the function is either a vertical translation, a vertical stretch, or a vertical compression. Okay? And then the last bit, remember I said if it's negative, so that was all the positive numbers. If I change it to a negative, see how it flips? Vertical reflection. Because everything's to do with vertical. When you have a negative, negative is a vertical reflection. But the theory is still the same. The larger the number, so that's currently 2.1. If I want it to be like a big vertical negative stretch, I just change that to negative 200, and it gets really thin. It gets stretched downwards. So the negative just tells you if it flips, and the larger the number makes it more of a stretch. Okay? Same thing with the compression. I can still make it a negative compression. I could do 0.01. And you can see there, the graph looks like I've compressed it vertically. Okay? That's what A does. All right. There's a lot of information so far, but that's why I'm trying to give you how the transformations come in. You've got left, right, up, down, and then you have vertical compression, vertical flip. Yeah? Last one. And that's it for today. And then we can have a look at some practice and graphs, as you can see. All right, N. Can you write in the notes for end here? N is the number that's multiplied to x. So again, it is a dilation. Same thing again, it's a dilation. That's the name for it. This is a dilation as well. So it's a stretch. But different this time, because you're affecting the x coordinates, this is called a reflection, but horizontal. It's a horizontal reflection, and by the same idea again, if n is bigger than 1, it becomes a horizontal stretch. This is a horizontal stretch. The larger it is, the more it moves away from the y-axis, the more you stretch horizontally. If n is between 0 and 1, so it's a fraction or decimal, just like A, this becomes a horizontal compression. But what's interesting is you can see the difference between horizontal compression and vertical compression. So when I show you on the graph, you can see the difference. Just look at the y-intercept. Because the y-intercept is at 0, 1, if you multiply the x coordinate, because it's 0, it doesn't change the y-intercept. It just compresses as well, but the shape will look different to a vertical compression. Yeah. Very good. If it's negative, so It's when it's going to be a reflection. So like this one, reflection is when the number for A is negative. Then for this one, it would be when N is negative. So that's a horizontal flip. This is a vertical flip. Yeah, so one's reflecting vertically, and one will flip horizontally. Okay. So I'm going to write horizontal flip to help you remember that too. Okay, let's have a look. So remember that's the vertical compression. Let's have a look now at N. So now I'm finally putting the last bit that I was missing before. Here's my N. Let's have a look at N. I want you to look at the y-intercept. The y-intercept is the most special one. So have a look at the y-intercept. It's at 0, 1. Watch what happens when I change N. So I said the larger the value, it should be a horizontal stretch. Watch what happens. See that? Actually, I forgot to mention, it's actually the reverse. Remember when we did chapter 7, the larger the number, it actually is a dilation of the inverse. So it becomes a compression rather than a stretch. But can you see there? That y-intercept doesn't change. Yeah, so that y-intercept actually it's a horizontal compression. Sorry, I got this one flipped around. If you remember from chapter 7, it's the inverse. So this one should be compression, and this is stretch. Okay, so that's the difference between vertical stretch and horizontal stretch. So the vertical stretch would have changed the y-intercept. Horizontally, in this case, it won't. If you change that N value, all it does is it makes it squash towards the y-axis or it moves away from the y-axis. So if I want it to move away from the y-axis, then this is what I'll do. I'll make it a decimal. So somewhere between, say, 0.5. See how it looks like I'm stretching it out further away? If I made it 0.4, makes it a bit wider, 0.3, 0.2, 0.1. You see how it's getting pulled away? It's horizontal stretch. Yeah. If I want to make it even more, I can make it 0.001. So I go 0.001. You see how it's now, it's still a horizontal, where is it? Wow, it's so big. Oh, there we go. Okay, so you can see I'm stretching it horizontally. But what's special is, same thing, if you look at the y-intercept, it's still 0, 1. Doesn't change. Because the n value is multiplying to the x, and if it's x is 0, it's always going to stay at 0. That's why. Okay, so n is responsible for that. All right, team. Those are the 4 key parts of the transformation that you need to know. That's 13C. Let's fill in some points, and then I'm going to get you to practice to tell me dilation, whether it's a vertical stretch, horizontal stretch for each one. But when I do, just fill in these points here. So, asymptote. What are key features? You have to have a y asymptote. Range. We can see that the graph never touches 0, but it goes to infinity. We can see that the domain can be any value. You can put any x value in and it's fine. So meaning it can be negative infinity to infinity. Okay. We can see that the y-axis intercept is always at 0, 1. A lot of information there, so the better you understood chapter 7 from last unit, the easier it is to understand how this graph works. Okay? I'm going to pause the video. I'm going to let's give you 5 minutes, digest the information, and you can talk to the person next to you, but I want you to predict. And if you want, you can use Desmos too to see if your prediction is correct. But I want you to look at the equation here and break it apart. What's the 1 do? What's the negative in front of the x do? What's the plus 1 here do? What's the base 2 do? What does the times positive 3 do? have a prediction of what changes. Where would your new asymptote be? Would it affect your y-intercept? Would your y-intercept change? What kind of reflections would you have, if you have any? And if you had a dilation, which is a stretch, what kind of stretch is it? Is it a vertical stretch, horizontal stretch? Have a guess, have a chat, decide what you think it is. Check on Desmos if you like. Here we go, I'm going to start recording again. Here we go, what you should have got, +1. +1 should tell you up by 1. So that, what does that change to the graph? It means the asymptote changes. Remember, the original asymptote is at y = 0. If it goes up by 1, then I expect a horizontal asymptote at y = 1. What's the next thing? I can see there is a negative in front of x. That's your n. N equals -1. So n is your horizontal flip. Okay, if it's negative, so it will flip horizontally. So instead of it looking like this, the graph now should flip like that. So it's a horizontal flip. So whatever's on the left becomes the right, whatever's on the right becomes the left. Yeah, so it should be this shape. That's my prediction. But then there's a +4, so -x + 4. If you want to know if it moves left or right, let -x + 4 = 0. Solve for x. So -x equals -4, and then x equals +4. So you should have had the graph should move right by 4. So that means this graph here, if it moves to the right by 4, it may just look something like that. Most people can't tell. But the key part is the y-intercept. The y-intercept would have changed. Okay? And then finally, what does a 3 do? 3 is a vertical dilation, so it's a stretch. So you can expect it dilates vertically, it stretches larger by a factor of 3. So that means when we say read the transformation, it should be dilation of factor 3 from x-axis. So I expect it to move away from the x-axis because I'm pulling it. Okay, so I'm pulling it by a factor of 3. Reflection. I gave you a horizontal reflection. So that's a reflection in the y-axis because it's flipping horizontally. Translation. We found that it moves to the right by 4 and it goes up by 1. Asymptote. The fact that you went up by 1, any vertical translation will affect the horizontal asymptote. So it now is at y = 1. Y-intercept. We can tell it changes. It's not 0, 1 anymore. I mean, the fact that it's gone up by 0, 1, it couldn't have touched at 0, 1. Okay, so that means I still need to find the y-intercept. How do you find y-intercept? We always knew y-intercept occurs when x = 0. So sub in 0y into the function to solve for the y-intercept. So here's my function. Y = 3 times 2 to the power of -0 plus 4 plus 1. You get 3 times 2 to the power of 4 plus 1. 2 to the power of 4 is 16. So 3 times 16 plus 1. 3 times 16 is 48. 48 plus 1 is 49. So you should have a y-intercept of 0, 49. 0, 49. This is the prediction. So we haven't typed on Desmos, but that's roughly what I expect the graph. Now, the difference between 1 and 49 must be really high, so I reckon it's a really thin graph that goes all the way up, and there should be an asymptote at 1. Yeah.
How do you illustrate the dilation of 3? Do you have to do something to show it?
Your textbooks would want you to pick a random point. So you said when x = 1, you sub it into that. That's a way to show it. When you're doing it full stack, it doesn't matter, because no one can tell. The only time it matters is if you sketch two different graphs on the same axes, then one that has a 3 and then one has a 2, you have to show which one is the thinner one. Otherwise, if you're sketching it as it is, don't worry about the dilation factor 3. So let's have a look if the answer is correct. So we expected y-intercept at 0.49. It should look the other direction, so a horizontal flip, and it should have an asymptote at y equals 1. Let's see. So we type in the equation. We say we've got 3 times, what was it again? 2 to the power of negative x plus 4 plus 1. And let's see. Y asymptote should be at y equals 1. Let's change that to a red line with a dotted. Here we go. We can see the graph never touches y equals 1, so that's true. So we're correct so far. And you can see the graph has been reflected horizontally. It has moved across to the right. We just can't tell that it's 4, but we know it's 4. And the y-intercept, clear, this is 15. So I said I had to shoot up really high. It should be at 49. So here we go. 0, 49. There it is. So if I actually zoom out a bit, that's what the graph looks like, which is what we predicted. We predicted that y-asymptote at 1, y-intercept, shape of the graph, 3 marks. Okay, so there's no x-axis intercept in this case, but what I was trying to get you to do is you can predict what the graph looks like from reading the transformation. Okay, that's it for today. If you want to have a go with the next example behind the sheet. I'll write up the solutions. Check with Desmos or your CAS calculator. But that's so you can see. Because half is the same thing as writing 2 to the power of 2 to the power of negative 1. Y is 3 together. So the negative 1 times x. 2 to the power of x. Exactly that. That's how they do it. Every time it's a fraction. No.